Hi, good morning, everyone. I'm Pooja, and along with my colleague Rakesh from AWS Professional Services, we help the customers migrate the data and the workloads to the AWS cloud as such. So today's topic is just to be mindful about the query optimizer differences between PostgreSQL, Oracle, and DB2. Yeah, as part of our agenda today, after a brief introduction, we would talk about DB2 and PostgreSQL, then Oracle and PostgreSQL, followed by a question and answer session. So if you have any queries during the session, we request you to please park it till the end for the Q&A session. I mean, we'll leave enough time for that one. I recently read this very old white paper from 2011. It was by Oracle, and it talked something about what makes for a successful data migration project. Now that paper, although it's very old, it is still relevant in today's times. So it spoke about how these migration efforts are often the necessary costs. I mean, we do want to migrate from the legacy systems to the modern systems. Now, whether it is at the application level or database design level, database engine, the underlying operating system, hardware, etc., etc. Now, the paper, I mean, what it said also was that around 75% of these new systems, as a result of the migrations, they fail to meet the expectations. And that is often because of the flaws in the migration process itself. That number 75, by the way, they have now revised it to 80% as per their more recent white paper on the same topic. The reason for the failure could be many, but one of them could be the misconception that migration, whenever we talk about the data migration, it involves only the copying or moving of data from, say, on-premise or the existing system to the new systems. And so we take all the efforts to make sure that none of the data is ever lost or scrambled on the way. What we forget to realize sometimes is that these days the systems are quite complex. So along with the data and its ancestry, we also have to make sure to ensure the quality of the data at all the levels and at all the stages, whether it is at the generation or storage or retrieval level. So, and that's why we have to start focusing on the performance aspect as well, like the performance of the queries that are run as part of the applications and their workload. So we have to focus on that as well. To understand that, we need to also know if you are migrating from system A to system B, how do these systems work internally? So that then we can go back to the root cause and see if there is a performance mismatch, then to resolve it. So to start with, I would request Rakesh to help us understand the differences between compilers of DB2 and PostgreSQL. Rakesh.
Thank you. Good morning, everyone. I hope they had a good picture. Just finished. So to start with, so when we are talking about migration, so this whole presentation would be focused little bit from migration, right? When you are doing migration from either DB to LEW to PostgreSQL, Oracle, DB to Oracle, DB to okay, okay. So sorry, I lost thought. I'm sorry. Yes, so the talk is focused majorly on from migration perspective, right? When you're migrating from Oracle or DB to LEW to PostgreSQL. So we talk a lot about schema changes, we talk about lot of data, right? Let's talk about before you even take the journey. Is there something that you want to be aware that, okay, this is how my SQL in Oracle would have worked, this is my SQL in Oracle, LEW should have worked, and this is not behaving the same in PostgreSQL. Why it could be, right? In Oracle, I used to get errors at the start, but in PG, I'm getting at the runtime. Why is that, right? So we're trying to cover those questions, and that should make your migration journey a little bit more smoother than what without it would have been, right? So let's get on to it, right? The first, right? So this is a picture by Bruce, right, on the left. And it's a very well-known picture, right, where a query goes through different phases, and on the right is the comparative, the same set of steps on DB to LEW side, right? So if you look at it, from query, let's say it comes from to DB2, right? The first thing that happened in both is parsing. So I'm skipping the main PostgreSQL and Postgres and those client side, but let's come, that query has come to the parsing stage, right? So what both the engines does is they parse the queries into different keywords and make different and create that graphs. Right? Then in DB2 side, if it is procedure functions and everything, it checks the semantics, and it checks the semantics for both, whether it's a code or a symbol select instead of update delete, right? But in PG side, there's a traffic code that decides whether there is no semantics check as such, but there is a semantic analyzer. If it is a simple select, it will tell you whether it is semantically wrong, right? I hope you guys know the difference between a syntax and semantics. Like syntax is basically whether you have written group by, before order by, and all that. Semantics is whether you have access to that particular table or not, whether the column that you're using, right, is compatible to the value that you're doing. For simple SQLs, this works, right, in both. So for simple SQL, the semantic checks happens in both, right? But when compared to PLP, that process is missing in PostgreSQL side, right? So it compiles the code, but it does not check what you have written inside, right? Even if you say my father is Godfather, it will just compile and keep it, right? But when you actually run it, that's when it says no, your father is not Godfather. It was a movie made by someone, right? So that's the error, right? So that's one big difference. In DB2, it checks at the time when you're trying to compile it itself. So just think. So now bringing this into migration perspective. So when you're actually migrating, converting the code, it's very important that you incorporate unit test cases and functional test cases in your migration journey at the compile time itself, not at the time when you're doing the integration testing and all, right? So that helps, saves a lot of time, right? So that's one. In both the sides, there are rewriting of the query that happens. Then rules are there present in both the engines and everything. So based on that, a query is written. And in DB2 side, there's something called query graph model that is used to create a plan for that. And once the plan is created for the SQL, it is stored in the memory, and then out of that one, there's a executable plan that is created. In PG, it is not stored anywhere in the memory, it is used. So every time you run the same SQL, it will create the plan again based on what is the underlying stats and everything. So that's again a difference, right? Now, once that plan is stored and when you execute, you both have executor engines and they execute the plan, right? In DB2 side, you can use explain table if you know. I don't know who all know DB2, but there is something called explain table that tells you what was the plan that was used for this query, right? Which could be different from the plan which is used for execution a little bit. So what it is, you can use in the executable plan through DB2 explain. So that's one difference, right? Then when you want to see visually, there is something called DB2 exfmt that you can extract the plan and see visually, and then there are tools also, GUI tools that you can use in DB2 side, right? In PostgreSQL side, I'll cover the tools, but let's say if you want to see what was the plan that, or what was the explain or the execution plan that was used by the query at the runtime, there is something called auto explain parameter. You turn it on, and the execution or the path that query took for your in PostgreSQL would be put in the log files. So and you can use that, and that's a very important thing, right? In many of my troubleshooting steps, right, the plan that is shown at the when I use explain analyze is different to the one that is used in the executor. So it is very important when you are in your testing journey, use this, set it to 1, and then set the parameter that if my query is running for more than 10 milliseconds or 20 milliseconds, so that I know what the plan was actually happened. So those two parameters will help you great to understand what your query went through. So that's an amazing way to do it, right? Then there are some of the factors that affect these plans in both, right? So I'm comparing both. So I'm just taking two factors, but there are numerous n, like how much memory you have and x, y, z, right? First one I'm talking about is optimization level. So folks from DB2 would know that there is something called optimization level that you can give. So the amount of time DB2 optimizers spend to come up with the right plan is higher. So basically the planning time is higher, but you get a better plan out of it. So the levels are from 0 to 9. But in PG side, there is nothing called optimization level. So it's always, it try to find the best plan possible. And there are factors like join collapse limit and from collapse limit that like little bit affected, but not to a amazing value. So expectation is that it needs to come up with the best plan at all the time, but based on the number of join conditions, where how many in and from clauses you have, so based on that and these three, it might pick up a little less optimal plan based on what value those are and reduce the planning time. But the in most of the situation that it goes for exhaustive search to find the best optimal plan for you, right, in PostgreSQL. A second factor that affects your planning is stats. DB2, we rely majorly on the run stats command to find out the relation between different columns, how many indexes and everything is there, and that is stored in the DB2 system tables. In PostgreSQL, there is command is called analyze, not run stat, analyze who are not, right. In that you can there are different if else clauses, like clauses that you can add and get it, but the major thing that I want to highlight is default stats target control, right, which is basically a sampling size, that how much of the table would be sampled for it to come up with the stats for your SQLs to run, right. Default is 100, which is 300 multiplied, right, that's a number. You can go a little bit higher if you think your stats are very different from what you actually see, right, but recommendation is usually default works. For OLAP systems, this can go a little higher. For small system, small database, this can even go a little lower, right. Then there is one factor that affects your SQL is correlation between tables, right. In DB2, there is something called extended stats, right, that you can collect and it captures those correlation. In PG side, there is no extended stats there, but you can, what you can do is you can create stats objects which captures the correlation between tables, and when you run the analyze command next time, those correlations are captured and used in your SQLs, like SQLs like where you say, typical example, right, zip code and city. Zip codes and city are one-to-one mapping. So if you say zip code is this, then city would be this, right. So they are correlated columns. So you don't need to, so if you have a correlation built on it, so zip code is this and this, that means, and you have created a correlation on them, then the one filter would itself give you the answer that you're looking for. But just be mindful that if you give the right correlation, SQL works, right. Let's say where city is Delhi and pin code is 110045 works, but let's say you say city Bangalore, pin code 110045, that query will actually return 0 rows, but your plan would think it is returning 1 row, so that would be a little different, right. So just be mindful of that. Now going little bit on the explain. So on the left is how the output from DB to EXFMT tool looks like to you, right. So if you look, these are the tables, sorry, maybe this is little blur, too much blur. So these are some of the tables that we used to capture this. So on the left you will see that a table scan has happened, then there is a join, hash join is happening with the third one, then combine that node is coming up with hash join and fetch is happening, and then that's the total cost on the top, right, total cost and IO. So this is the total cost and IO that is coming out to be, right. So that's how you if you are from DB2 background coming to PostgreSQL, this is how you are used to reading this information, right. In PG side, you should we'll see a difference, right. So this is like typically how DB2 not DB2 explain and analyze command output would look like. So you see hash here, it is doing hash for it, then it is doing hash join, and there are conditions on it, right. So I have the same in graphical way, maybe better picture. So there you will see the gather cost and everything, and how many rows it fetched, what was the actual time and everything. In DB2, if you don't have WLM setup, you don't know the actuals, right, it is estimated. But if you have WLM setup and those classes are set properly, you will get actuals also. For my test, I did not do it, so that's why you don't see actuals. In PG, you will see estimated and actuals also, right, both are present there. Then these are couple of tools that are present that you can use them to visually explain in PostgreSQL, right? So one I used to use a lot is DeepZ. So here if you put the output of your explain and just dump it there, what it gives you is it asks you for a permission whether can I store it for future references and rest of the world can see that. If you don't want, just don't select it, right? So here the red ones are the ones which you need to focus on, right? That these are the costliest part of your explain, and how you read is bottom to up, right? That's how you read. This is exactly the same in a tree structure. So here this is the tree. These are the costlier ones which you can go through and identify what is the problem, where is the problem in my explain, right? So this is couple of visual explanation tools that are available for PostgreSQL, not natively, but is it's open source, so people are more than happy to contribute and for everyone else to use. Next is I want to talk little bit about predicate handling, right? I hope we all understand predicates, right? Okay. So in DB to LUW side and Postgres, both worlds, there are I have divided it into three major category. One is range delimited, then index archival and data archival, right? So I just want to know, do you know theoretically what they three are? Like if you don't, and then I will spend little bit time on explaining them also. Do you want me to take some time and explain them? Okay. So first, right? What is range delimited? So let's take an example. Let's say your table, simple, right? It is true in both. You have a table and you have an index, right? Index, let's say, is on table has 10 columns, index is on 2 columns. Let's say column X and Y. When you say column X equal to 10 and say column Y equal to 20, right? So basically what you're saying is you have giving a start and stop value for your query, for your planner to know from where to start and where to end, which X for 20, Y equal to 20, right? So here the start and stop key both are 20, okay, based on X and Y condition. So that's a range, right? In another term, if you want to say that, you can say between 10 and 20. Let's say X between 10 and 20. So you have a start key, you have stop key. So your planner knows exactly from which page to start and which page to end it. So those are called range delimited ones, right? Or access predicates in PG side, right? Same concept. So how do you, so if you are coming from DB doer, right? So if you use to your EXFMT output for a SQL which is using this range delimited one, you would be seeing a start key predicate and a stop key predicate, right? Which will tell you what was my start key and where did it end it, right? So that's how you used to come to PG side, right? It does not say what was my start key, what my stop key. What it says is what is my index condition. That's, and it is left to you a little bit on you to identify whether it's really range delimited or do I need to put some changes. And here it is not a big deal, but as soon as those index filter become index archival or index filter predicates, it becomes a big deal, and I explain you in detail why. So let's say your SQL says you're again saying your index is on X and Y, and let's say you say Y equal to Y greater than 2000. So what does that mean, right? It cannot know from which page to start and which page to end, even though it is an index column, but greater than 2000. It knows for second column I need to start from here. So for first column pages, it needs to still scan those index pages and then come to the second one to identify which is greater than 2000. That's my index archival. Even though the conditions, so it will say archival predicate in DB2. So people from DB2 were used to that information. Okay, if it is archival predicate, I need to put a little bit thought on my where conditions and all that stuff, right? Can I rewrite them? Do I need to make changes? In PG side, it is still shown as index condition. It does not show that it is scanning those index pages, right? It is index condition. So you need to put a little bit thought what kind of conditions that are using, right? Here, there that information was, it is not. For 10,000 rows, it does not make a difference. but it makes a difference when it needs to scan those 10 million or 20 million rows. So there's a huge difference in the planning and the execution time between this one and that one based on the information that you are seeing. So little bit cautious on that what kind of predicate filtering actually it is getting applied, right? Third that I'm saying is data searchable or table level filter, where basically you are applying a filter which does not have an index, right? So this is sequential scan, and then it will just show as filter condition. There also it will show as searchable predicate, and then what is the filter condition. So no index is present on it. So these are three major categories. You can go further deep into it and identify okay residual and all that stuff, but it will be deep. But these are three major categories. So focus should be on index searchable ones, right? When you're looking, if your SQL is not amazingly great and not working, maybe think, even though your explain plan in PG side might be showing you that in index condition, but it might be scanning the whole index, which is costlier, right, compared to the sequential scan, right? We know the sequential scan cost and the random page cost, right, which is 4 times the sequential cost. Still it goes because, you know, right, BT indexes. To get to 1, you need to do 2-3 hops extra than sequence, right? So just be mindful of that, especially in the index predicate side. These are the major explain operators that you will see in DB2 LUW and PostgreSQL. There can be 10 pages of it. I'm just capturing the major ones, right? I think we all know what is table scan, what is the equivalent in PostgreSQL side, which is sequential scan. Index scan is index, right? IXEND, what is IXEND? So if let's say your condition is such that your optimizer can get, or the execution plan can get a better output by using 2 indexes to fulfill your condition, right? Let's say where joining, right, between 2 IDs, and it used both the table indexes. So that is shown as IXEND in DB2 side, but it is bitmap and in PostgreSQL side, right? So this is the comparison I am saying. So and or, right? So basically if you have or conditions and all, so equivalent one is in bitmap or in PostgreSQL side. So there is something called joins, right? We all know merge join, hash join, and NL join, right? NL is very frequent, but you can force it to use hash join in DB2, same here, based on how much memory you have, right? So for in DB2 it is used as shown as MS join, but if you come in PG side it is shown as merge join, right? NL join, then nested loop join with filter conditions, right? So what was the merge condition that was used in PG? In DB2 side, you guys might have been used to seeing those conditions and all, right? But here it is shown in the join, below join there would be a line statement saying what was the condition used to show that. Same goes for NL, same goes for hash join, right? The usage of hash join is like always debated whether should be hash join be used or NL join would have been used, but it is like what we all DBA say, it depends, right? It depends on the day whether it was raining or it was a sunshine. So based on that it can do that. So then there is something called group by, and PG side it is shown as group by key. Sort, right? In DB2 whether it's using index or not, it just, if it is a sorting order by a group by, it has a sort clause in it, right? In PG there is 2 operators that you could see. One is sort, one is incremental sort. So the difference is the whole result set is sorted at one. Incremental is the piece which needs to be joined between that node is only sorted instead of waiting for the whole sort to happen, right? So that's different. And last is the filter, like what kind of filter was applied and all that. So this is me ending, and I am handing over to Pooja, right? And I'll take questions at the end, right? Thank you, guys.
Now for Oracle and PostgreSQL, Rakesh has already explained to us about how the PostgreSQL optimizer works. So I would not be spending much time on it. As for Oracle, it goes to, like whenever we pass in a query, so it goes to the parsing phase first. Parsing has 2 major components, the syntax as well as the semantic check. Once it passes the syntax check, and I would not go into what goes into the syntax as well as semantic, but once these two checks are passed, then a hash value is is the outcome there. That hash value is then checked if it is already present in the shared pool of the memory. Why do we check that? Like in case you had run the same query earlier in the same format. Yeah. Okay. I hope I'm audible till the end. Okay. Yeah. Okay. Sorry. Yeah. So syntax check, syntactic check, and then the hash value is created. It goes to the shared pool part of the memory to check if it is already there. And why would it already be there? In case you have already executed the same query earlier, it would have the same hash value. Now you have to be again conscious of the fact that here the case itself matters. So you might have run select star from EMP in lowercase earlier, but now you're running it in the uppercase. The hash value would be different in the case. Let's say it finds it, and if it is there, it would also be having the execution plan of the query stored there. In that case, it would skip the optimization part of it, and then before go directly to the execution. Just before the execution, it will also check for the context of the query. Like in case you already, say user A is running select star from EMP, wherein EMP is in their schema, and user B is also trying to run the same query where the same table is in their schema as well, but separate entities. So despite the query being the same, hash value being the same, it will not go for the same execution plan in that case because the context is completely different. Now, in case it doesn't find the query or the hash value of the query in the memory, then it has to go to the optimizer phase. Now, in the optimizer phase, you have this query transformer. So you can again relate it to what happens, say in PostgreSQL, like you have the query being rewritten if you are specifically using views or subqueries that way, and then multiple execution plans are created. Now, a very common analogy is given about how the GPS system works, and multiple paths are created for going from a source to a destination. Similarly, here also from a query to its results, there could be multiple paths. It could maybe take an index, it could maybe go for a full table scan, and so on. So these different plans are assigned certain costs to it with the help of the estimator. So the estimator will estimate the cost. Again, it needs certain data to give it that value. Just as in case of GPS, if you want to know the cost, that is the time taken for the one path, you would need to know what are the traffic conditions and what are the roadworks going on, roadblocks, and so on. So here also it needs that data, and in this case the data has to come from the database itself. For example, if there is a table, how the data is distributed within the table, whether it has indexes or not, and so on. So this data it requires to assign the cost to the query, to the plan of the query. And amongst all the different plans that are created, one which would be the most optimal one or the lowest cost would be selected, out of which the row source generation program would be creating the row source tree and finally getting executed. Now we keep talking about the most optimal plan having the cost, the least cost, but what exactly is this cost here? So in case of PostgreSQL, it's just a sum of the startup cost as well as the run cost. Startup cost is nothing but the one which is incurred right before the first row is fetched. So if let's say you're going for a full table scan or say sequential scan in case of PostgreSQL, then it doesn't have to put in much thought. I mean, it can directly start fetching from the first record itself. So the startup cost is almost equal to 0. And the run cost would be the cost of running all the rows, I mean fetching all the rows. Okay, just one more thing in startup cost. In case you're going for say index scan or you're going for a sorting thing, then it does have to apply some effort in order to start the execution. So that comes in the startup cost, which might be more than 0 in the case. For Oracle, we don't have any straightforward formula as such, but we know that it does depend upon the I/O cost and the CPU cost and the communication or the network cost that might be there. Now all these are again estimated by the statistics or the data that you provide to the optimizer. The units are arbitrary, so I can't say that this cost directly represents the time taken for the query to execute. It doesn't. And also this is more for the comparison of plans between the database itself. Let's say if I have a cost assigned to a plan in Oracle, say 100, and in Postgres it comes to 200. Can I compare? I mean, it might be the same query for the same set of data, but can I say that in Oracle it is running faster than PostgreSQL? Well, not always, because this is relevant for comparison within the database only. Now we again cost. It depends upon the statistics that the optimizer gets. So how do we get this the statistics? Now in both the engines, both Oracle and PostgreSQL, there is an automatic stats collection that goes on in the background. So in case of Oracle, there is usually the scheduler. I mean, there's a scheduler job which takes care of it. So you have the stats getting collected at a particular window, the maintenance, I mean, for the stats collection. Where in PostgreSQL, you have the vacuum job, auto vacuum job, which goes and collects these statistics. So usually we can say that these automatic stats collection should be enough for an average workload kind of situation. But again, we know our data better, we know our systems better. So if we feel that these are not enough, then we can play around a bit with the global settings or some settings at the table level. Again, depending upon the peculiarities of the table that there may be. So we can play around with those tables. For example, in Oracle, usually it collects the stats for the tables when the stats become stale, 10% or so. You can always reduce it to 2% or 3%. Again, the overhead would be high in case you want the stats to be collected for a large number of tables or for the large set of data. So again, depends upon the sampling as well. So auto stats all good, but again, if you want to kind of add on to it using the manual stats, again, either add on or replace the auto stats completely. Then in Oracle, you can use the dbms underscore stats package, and in PostgreSQL, you can use the analyze as well as the other one. And again, these stats can be collected at index level and table level, schema level, dictionary level, and database level at the Oracle side. But for PostgreSQL, we have them at database, table, and column. Now, even in PostgreSQL, we can change the settings at the table level also. You can change certain parameters at the table level also in order to just manipulate the way these stats are collected or the frequency with which these stats are collected. This might depend a lot on how your workloads are distributed. So you can take a guidance from there. Now, stats, again, we have these data distribution stats. Again, you have to also understand if your table has columns which might be correlated. You might have taken care of it during the normalization phase itself, but in case you do have the correlated columns, then you can go for the extended stats as well. The extended stats will take care of the say 2 or multiple columns and understand how the data is distributed amongst them as there. So with all this, we are kind of sure that the optimizer has enough data to make the decision as in which plan to choose. But still, especially in Oracle legacy systems where many people have used hints, not the most recommended one because again, we want to trust the optimizer here. But still, due to certain reasons, if you are, let's say, on-prem or the source system is Oracle and you want to migrate to PostgreSQL and you want to continue using the hints, before that, see if you can go to the root cause of the problem, performance problem, like why were the hints used in the first place. If you still want to use it while you're troubleshooting or while you're going to for the root cause, you can have those kind of, not the exact one-to-one kind of equality there, but you can nudge the optimizer in the PostgreSQL as well. So you can, again, maybe set the cost of the sequential scan to be much more higher so that the optimizer is maybe misled or led to believe that the sequential scan would be more expensive than the index scan and it would then prefer the sequential scan to take place. So this way you can manipulate it. Along with that, we also have the extension PG hint plan, which can have not all the equivalent hints from Oracle to PostgreSQL, but some of them. I mean, Oracle has around 60 or so hints. So not all of them are represented in PostgreSQL PG hint plan, but still you can have some of them. But as I said, these hints, use them as path to find the solution and not the solution itself. Now, once we have run the query and again, we have the queries run with the plans, we can use certain tools to measure the performance there. So we have the SQLT in Oracle. It's more of a reactive in nature. So you have the SQLs run. You are concerned about their performance. So you can run this tool to look at various SQLs, what plans they were taking, whether those plans were optimal or not as per your understanding of the data. Similarly for PostgreSQL, you can use explain or explain analyze, and there are various other tools as well. There is one feature in Oracle that I might want to talk about, and that is the SPM. Here, if let's say you have a query which is taking a workload which is really heavy, and it was working fine all the way, but suddenly since yesterday it is not working well. That could be that somewhere the plan has changed. Now, if you go back and see that it was running with a previous plan, which was, the execution time was less, but now the execution time has increased. In that case, while you are again troubleshooting the real cause of it, you can pin that plan with this query until the better optimization plan comes in. So that helps us in case of the critical workloads and in the critical times to at least get by the situation while we are, going to the real cause of it. Now, we won't be able to cover all the aspects of the optimizer, but let's quickly look at the access paths and some very basic examples in Oracle and PostgreSQL. So for this example, we just created one table demo tab. For Oracle, we use version 19c, and for PostgreSQL, we use the version 16.3 here. In both the engines, we had the table created with 3 columns: ID, num data, string data. ID, this was populated with around 10,000 records, and ID was assigned as an index here. So the structure that you're seeing here is just a logical representation of the index and the table, not really how the data structure is stored internally. Now we just ran a query sum of the ID from the demo tab. Now, as expected, since ID is the indexed column and all the data is in this index, so it just needs to visit this index only to get all the values and do the sum of it. So as expected, we will see the index fast full scan in Oracle as well as index only scan in case of PostgreSQL. Then we run, select all ID from the demo tab. Now in PostgreSQL, as expected, since it knows that all the values of ID are in the index, it is fetching these values from the index itself. But it's slightly different in case of Oracle, and the reason lies more with the way the values are stored in the index for the table. So if you have a null value for ID here, so it might not be represented in the index. So when you run this query, optimizer feels that what if you need the value null also to be shown. So in that case, to be on the safer side, optimizer goes for a full table scan. So here it says table access full in case of Oracle and index only scan for the PostgreSQL. But what if we tell the optimizer that I don't even want the rows which have null values? So if you tell it explicitly in say a query saying that select ID from demo tab where ID is not null. So in that case, Postgres behaves as expected, goes to the index only and gets it. But in case of Oracle, it then goes for directly for the index because it knows it doesn't have null values and we don't even need null values there. So it uses a fast full scan here. Now, if I'm selecting all the rows from the unindexed columns, I don't have to explain it, like it will go for a full table scan both in Oracle as well as PostgreSQL. And if I'm going for the non-indexed one, non-indexed columns, and in my condition, I have used an equality condition, it goes directly to the record which might have that ID value, and from that it will pick up the corresponding row ID and go to the table using that row ID. And same in case of PostgreSQL, it picks up the CTID and goes to that one. In terms of equality, the conditions which say less than or greater than, the optimizer has to know how many records might be there, which could be say less than 4 in this case. If there are very few records, then it will go for the index scan. If there are a large number of records, then it would go for a full scan. Now again, it all comes back to the same thing: how well your statistics are collected, and if the statistics are not enough to tell whether it has less number of rows, then it might actually end up going for a full table scan even if it is not required here. So in this case, large number of records were required, so it goes for a full table scan both in Oracle as well as the PostgreSQL. Now again, we won't be able to cover the entire thing, but just giving an example of slightly more complex query here. So we have this query run on the same set of data using the same 5 tables in both Oracle as well as PostgreSQL. And we get the explain plan in Oracle, and we get it in the PostgreSQL as well. If I don't know if it's visible properly, but you can see the way the joins are placed, the way the scans are placed, that might be slightly different in case of both the engines, and that is why we need to understand whether again, just because it is going in this way and that in the other way doesn't mean that this is better than the other or that is better than this one. So we have to test for the performance there, and in case you want to manipulate it, again, stats and the hints, or I won't call it as direct hints, but manipulating the parameters could help it a bit. Yeah, I'll end the session now. If there are any Q&As, we can take that.
So, two slides before, there's a null column, right? I mean, the way it's been searched in PG engine versus whatever. So, null column. So, before even I ask a question, is this the primary key?
No, it's not the primary key.
It's not, okay. So, here you have one-to-one mapping. It seems there is some null pointing to ID 5. I think that's not the case. It should be mentioned on the other side. Right? I think if you
Oh yeah, that is yeah, that is a mistake.
more than one null column, which means it has an address for all the rows, and that's how it's going to
Yeah.
go, right? Okay, got it.
Yeah.
I was a little confused with the value and this.
Yeah, sorry, I would take care of that one.
Yes.
Sometimes normals happen across the environment that the same query gets a different execution plan.
Yes.
And then most things happen in the production and we get surprise. So in Oracle, the SQL team helps us to bind a query with a specific execution plan. So how can we achieve this thing in
As far as I know, it is not there in PostgreSQL, but I think Aurora PostgreSQL does have that, right?
Yeah. So open source, there is no binding, right? So it, as I said, the plan is not stored in memory, right? It is always at the runtime based on the stats and everything that is there. There are some commercial engines like Aurora PostgreSQL. They have QPM that helps you do it, but open source community. Sorry, as of now not there, but most likely in roadmaps. And yes, sir.
We create indexes for multiple columns.
Yes.
Table and so we have big map and postgres.
Right.
So which one would be better for large tables?
Sorry, compared to what?
We create two types of index. Okay. We create indexes multiple columns.
Right.
Single index.
Right.
And we also have bitmap and right.
Right. So bitmap and is an operator. That is an operator. That means that, let's say you have two indexes and your where clause is something like where a equal to this, and there is a join, and then right. So what it is using is two indexes. It is using to fulfill your answer. So instead of just using one index and doing a sequential scan on the other one, so it use both the indexes, get the pages, go to the table, and then get you the answer. So it's a bitmap is an operator, not an index. Yeah, it's operator.
Okay. But we create a single index, single column and single index, as a multiple indexes, all components.
Oh, so your question is, let's say my where condition is x, y, z. That's my where conditions, right? And instead of creating one single index, which is x, y, and z, you are saying whether it should have just x, just y, and just z. So let's say your SQL is large table. So see, what is your queries, right? Is it just where x equal to something? Then that one index is, then that whether it's a multi-column index or a single index, same. But are you using where y equal to some values more, or are you using where z equal to, what is your workload looking like, right? Which index, which column is the most used? Maybe, see, this is my personal experience, and everyone has their own personal experience, right? Okay, sure. So, sorry, I'll talk to you, but it is like I would say based on their workload, multi-column makes more sense than just single three indexes. It affects your insert updates, and given that MVCC, there are lot more other consideration to be happening. All right.
One last question.
I'll take outside.
Yeah.
Thank you.
Thank you, everyone.
Thank you.
Thank you.